See this problem. A uniform magnetic field of 1.5 Tesla exists in a cylindrical region of radius 10 centimeters. Its direction parallel to the axis along east to west. A wire carrying current of 7 amperes in the north to south direction passes through this region. What is the magnitude and direction of the force on the wire if the question A is the wire intersects the axis? Question B is the wire is turned from north-south to northeast-northwest direction. C. The wire in the north-south direction is lowered from the axis by a distance of 6 centimeters. Our motive is assume that there is a cylindrical space like this. So there is a uniform field which is accumulated under this cylindrical shape. So assume that this is the axis of that cylindrical shape. So at this axis, if we keep a current carrying conductor which is normal to the field and some current is passing through it, so we need to find out the effects of magnetic field on that conductor for these three different cases. The field is moving from east to west and the current is moving from north to south. So this can be called as northeast and this can be called as northwest and this can be called as southwest. So here the current is making 90 degrees with the axis of the cylindrical field. This is the first case. And the second case is, if you see the problem, the wire is turned from north-south to northeast-northwest. That means the conductor is turned to this direction like this. This is northeast and this is northwest. That means it is parallel to the field. But here we come to know that one big mistake has done in the question or else in the answer given in the textbook also. In the question it is described like northeast and northwest. If it is northeast northwest, this is look like this. So at this position the force experienced by the conductor will become 0 because the current is flowing in the direction of the magnetic field, so no force will be experienced by that conductor. But in the answer given in the textbook, it is described that it is making some 45 degrees with the field. That means it has to turn to northeast to southwest, but here it is mentioned northwest. So if we consider this, force will become 0. If we consider southwest, you will get the answer which is given in the textbook. So we will consider that case also. So that the conductor turned into like this. And third case is it has lowered to some distance. If we consider this is the center of that circular surface of the cylinder, so if you lower this one, till now it is touching the axis of the cylindrical field, but here you are lowering the conductor to some distance. So we need to find out the force experienced by the conductor at this point. So these three are the motives of this problem. One is when the theta is equal to 90 degrees, we need to find out the force. When theta is 45 degrees, we need to find out the force. And when theta is 0, at that moment also we need to find out the force. And if you move away from the axis of that cylindrical field, that force also you need to find out. So these four forces we need to find out. So that is our motive. Now come to the investigation part. What are the quantities that I have given? The magnetic field B is given. B is equal to 1.5 Tesla. And the radius of that cylindrical field will be R, and that is equal to 10 centimeters or 10 into 10 to the power of minus 2 meters. And the current passing through the conductor I is equal to 7 amperes. So these are the given quantities. So by resolving, we need to get the answers for our motives. Now come to the resolving part. The force experienced by the current carrying conductor when it placed in a magnetic field can be written as F is equal to BIL sin theta, where theta is the angle between the direction of the current and magnetic field direction. and L is the effective length. For example, if we keep the current carrying conductor like this, only this much is the effective length of the conductor due to that magnetic field. So this is the diameter of that circular thing. So obviously it is 2r. If r is the radius of this cylindrical surface, then 2r will become the effective length of the current carrying conductor. That is equal to, I am finding the force 1. Here angle made by the current carrying conductor with the magnetic field is 90. So BIL sine 90. So B, we know 1.5 Tesla into current 7 amperes into L, it is 2R, that means 2 into 10 into 10 to the power of minus 2, that is equal to, we will get 2.1 Newton. And come to other case like northeast and northwest case. Since the current carrying conductor is in the direction of the magnetic field, no force will act on that conductor. So the force 2, according to the given problem, force 2 is 0. If we consider the answer of the textbook also, then we need to find out the effective length first. So this is the effective length. So earlier this is small, but here it is more. So how to find this length, effective length? F3 is equal to BIL sine 45. 45 is like it is pointing north east to southwest, so it will become 45 degrees, and this is also 45 degrees. Sine 45 is 1 by root 2, so I kept it like that. Now we need to find out the length. Here if you see, this is R and you have 45 degrees here, so we need to find out this much hypotenuse. So we will get, this is adjacent side of the angle and this is hypotenuse, so cos 45 is equal to R by that hypotenuse. Then hypotenuse is equal to R by cos 45. So cos 45 is 1 by root 2, so this will become root 2R. This is root 2R. So if we consider the whole thing, that will become 2 root 2R. Then this formula will become BI into, in place of L I am writing 2 root 2R divided by root 2. Root 2 gets cancelled. So BI 2R, which is same as this. So then the value will become 2.1 Newton. Now we need to find out the force which is experienced by the current carrying conductor when it is kept 6 centimeters below the axis of the cylindrical field. I am taking a lateral view or cross-sectional view. So this is the center, this is the diameter, and you are moving the conductor 6 centimeters below the axis of the cylinder. This is 10 and this is 6. According to Pythagoras, we can find the value of this, like root 10 square minus 6 square, that is equal to root of 100 minus 36, that is equal to root 64, that is equal to 8 centimeters is the value of this arm. And the second arm, the whole arm will become 16 centimeters. So the effective length at this moment will be 16 centimeter. So your L becomes 16 centimeters or 16 into 10 to the power of minus 2 meter. Now come to the fourth force, B into I into L, that is equal to B is 1.5 into I 7 into 16 into 10 to the power of minus 2. With this I will get 1.68 newtons.